Good morning and welcome to my presentation of FABRID. This work is joint collaboration with Marc Wyss, Adrian Perrig and David Basin from ETH Zürich, and Vincent and Martin Strohmeier from armasuisse. Unfortunately, all of them are actually attending this conference. So let's start with our motivation. When we started our work, we realized that in the internet, users don't really have a lot of control how their traffic is routed. The internet essentially works as a black box. The user says the destination where it wants to send traffic, but has no way of specifying the internal or the interdomain path that is used to reach this destination. Furthermore, paths are not necessarily stable. Due to problems such as policy changes, link failures, or load balancing, paths may change even during the lifetime of a connection. And furthermore, as we've seen before with Grace's talk, paths can be hijacked. So an attacker can actually attract traffic that should normally not be routed through this attacker. What we would like to have is to be able, first of all, to send traffic along trustworthy devices, where the definition of trustworthiness depends on the sending endpoint. In this scenario, we try to protect against eavesdropping. But we have the first node on the path, as you see on the top, is actually eavesdropping. The typical approach to protect against this is to use encryption, for example, TLS. However, this doesn't hide any metadata, which means that the attacker can still observe packet timings and packet sizes and often infer the content of the data packets. Instead, what we would like to have is to be able to both encrypt and send over trustworthy devices and mitigate against such attacks. The second property that we want to achieve is to have strong geofencing properties. In this example, we have a sender in LA, a destination in New York, and we have two other networks, namely a Rogers communication network in Canada and Telmex networks in Mexico. The problem is that in the current BGP-based internet, the default path follows the lowest cost path. So it might be that instead of directly connecting to New York, traffic is sent via Rogers communication. Although we would prefer to stay within the US in this example. So the goals of our project is to allow network endpoints communicating via the internet to choose forwarding paths which meet their criteria in terms of which routers are used to forward traffic. As we've seen before, a possible criteria is to route traffic along trustworthy devices, where trustworthiness might, for example, be who manufactured this device. So it could be only devices manufactured by extreme networks. And the second criteria we've seen before is geofencing. For the example that we had, that you want to ensure that your data stays within the US. There are many other examples. One other criteria that is very interesting is to only route traffic along devices with specific hardware capabilities. So for example, you might want to send via PTP routers to achieve more precise time synchronization. But how can we achieve such interdomain device-level path control? One recently proposed new network architecture is SCION. And SCION allows the source essentially to choose over which networks their traffic is sent. So the source in LA, to ensure geofencing, can specify that he wants to send his traffic via AT&T and then directly to New York. This allows the source to choose both the incoming border router to AT&T and the outgoing border router, thus evading the Rogers communication network. However, one problem is that if you want to do geofencing, AT&T might have some nodes in Canada which might be traversed within this network. So SCION essentially does not allow you to choose any path within a network. In this example, we have two routers within AT&T, the top router, which is trustworthy, and the bottom router, which is not considered trustworthy from the endpoint's view. A different network architecture is TPR, Trusted Path Routing, which is currently being standardized in the IETF. And TPR is a very interesting protocol. It allows a network operator to use remote attestation on its internal routers and then exclude untrustworthy routers from the routing topology. So in this case, if the bottom router is considered untrustworthy, it would be removed and all traffic would flow over the top router. And our work essentially combines these two principles And this enables us to design FABRID, the flexible attestation-based routing on interdomain networks. So FABRID allows us to select which networks we want to traverse, and additionally, which internal routes should be selected in each network. Let me walk you through an example of how FABRID works. Again, we have a source in the left, network A, destination in the right, network D, and we have two intermediate networks, B and C, which each has two different internal routes, route 1 and 2 for network B, and route 3 and 4 for network C. Now, FABRID is split into two separate components. First is the control plane, which is used to distribute this internal route information to the endpoints. So in this case, network C would announce both routes 3 and 4 to network B, which would then add its own internal routing information, routes 1 and 2, and send it to the origin network, network A. Once the endpoint actually receives this information, it looks at its own criteria, how it wants to route its traffic, and selects appropriate networks, as well as internal routes within these networks. So in this case, the source endpoint would choose network B with route 1 and network C with route 3 to send its traffic. Then the endpoint encodes this route information into the packet header and sends the packet along this path, which allows each of these border routers of network B and C to route traffic accordingly. There are several challenges we had to overcome in designing this system. The first challenge was that we don't want to reveal too much information. So most network operators would not be comfortable to reveal their complete internal topology. Instead, what we do in FABRID, we ensure that each network operator decides how much information it wants to release via so-called routing policies. These routing policies are specified as first-order logic formulas, which allows them to be very expressible for the different use cases, for different network operators, as well as extendable for future use cases that we cannot currently predict. An example of such a policy is a network operator which says in its policy that all routers are manufactured by Extreme Networks and run the Extreme Network OS as a software. Let's highlight some relevant router properties, router policy properties that FABRID enables us to choose. We've seen a manufacturer before, and hardware, for example, hardware capabilities such as PTP. The software, including the versions at which they're running, is also a very interesting property. And geolocation to enable geofencing. And similarly, we can also use the jurisdiction, which can be used to ensure that data does not leave a certain jurisdiction, which is often important for example, military use cases. And the recent emergence of green routing also opens a very interesting use case, namely that we can look at the CO2 emissions of the different routers and route on such that we minimize these emissions. And note that the first three properties, the manufacturer, hardware, and software, can be actually verifiable by a remote router attestation, which is very similar to the TPR technology I explained before. Another challenge that we had to overcome for the data plane is how do we distribute this policy information to the endpoint in a scalable fashion while ensuring that there is not significant overhead. And we solved this by piggybacking this policy information on the existing SCION routing messages. So no additional messages, routing messages are necessary for FABRID. And we also ensure that we only disseminate changes in the policies because we expect that most policies will stay the same for a long period of time. So it's not necessary to re-disseminate them every hour, for example. And finally, we also reuse common policies among multiple ASes, which means they do not have to be distributed at all to the endpoint, or only once in the beginning. Finally, we have one more challenge we had to overcome, namely to protect the policies embedded in the packet header. Namely, we want to ensure that attackers cannot learn the policies and cannot modify them. We do this by encrypting the embedded policies and then authenticating them via a per packet MAC. Here it is important to note that we only use symmetric cryptography because we want to still achieve high throughput. And if we use asymmetric cryptography on a per packet basis, that would be very difficult. For the evaluation, we implemented FABRID using DPDK, and we showed that for the border routers, which have to decrypt the policies and then forward the traffic accordingly, we can achieve up to 160 gigabit per second with fewer than 16 cores. And for the endpoint, in order to generate FABRID traffic, we can see that we can, with one single core, we can achieve roughly 1 gigabit per second of traffic generation. So here on the left side, you can see kind of the worst case when we have an extremely long path consisting of 16 networks, and we have minimally sized or very low packet sizes of 100 bytes. But even in this kind of worst case scenario, we can still achieve almost 1 gigabit per second. And if we then go to a more realistic packet size of 1,500 bytes, we can achieve over 2 gigabits per second. So in conclusion, FABRID enables inter-domain device-level path control, and we leverage both SCION and remote attestation to achieve this. We enable many exciting new use cases, for example, geofencing, routing over trustworthy infrastructure, as well as routing over devices with certain hardware capabilities. And while FABRID needs support from network operators, as well as deployment of SCION, it is incrementally deployable, and it provides incentives for early adopters. Thank you very much for your attention, and I'm free to accept any questions.